Okay, in this video, we're going to be talking about section 2.3 that deals with graphs that enlighten and graphs that deceive. Okay, so let me go to the other camera. Okay, so that's the section we're going to talk about. This will wrap up chapter 2 about summarizing and graphing data. Now, in this section, we're going to develop an ability to graph data using a dot plot, stem plot, time series graph, Pareto chart, pie chart, and frequency polygon. And then we'll determine whether a graph is deceptive through the use of a non-zero axis or a pictograph that uses an object of an area or volume for one-dimensional data. Okay. Now, as far as all these graphs, we won't go into a lot of detail about all of them. What I'll be touching on in this video will be the stem and leaf plot, or the stem plot, and also I'll cover a frequency polygon, okay? Because that's where the homework is going to be based on just those two. I'll talk about the others in this video, but we won't do any examples of those. All right, so let's talk about graphs that enlighten. One of them is a dot plot. And in a dot plot, it consists of a graph in which each data value is placed as a point or dot along a horizontal scale of values. Dots representing equal values are stacked. So for the IQ scores of low lead group, here is what that dot plot looks like. So you can see dots are stacked on top of each other. That means that there is a data value that occurs more than once. Okay, so that's what a dot plot looks like, and do be familiar with what that dot plot looks like and what it is. All right, now the one we're going to look at is a stem plot, or sometimes it's called a stem and leaf plot. It represents quantitative data or numerical data by separating each value into two parts: the stem, such as the leftmost digit, and the leaf, such as the rightmost digit. Better stem plots are often obtained by first rounding to the original data values. Also, stem plots can be expanded to include more rows and can be condensed to include fewer rows. There are two advantages of a stem plot. One, we can see the distribution of data while keeping its original data values. And number two is this: constructing a stem plot is a quick way to sort data or arrange them in order, which is required for some statistical procedures, such as finding the median or finding the percentiles. Now, in the next chapter, we're going to be talking about finding percentiles and also finding the median. And you're going to find how important it is to have your data set sorted in numerical order, preferably from least to greatest. Now, on the next page, you'll see an example of what a stem and leaf plot looks like for the IQ scores of low lead group. Okay, so here your lowest IQ scores are, in this case, 50 and 56. And then here, these IQ scores are 111, 115, 115, and 118. Even though in the leaf here, the 5 occurs twice. You have to include that because the stem plot accounts for each and every single data value in that set. Okay, so now let's look at example 1. Here we're going to construct a stem and leaf plot of the test scores: 68, 72, 86, 75, 89, 89, 88, 90, 98, and 100. And how do the stem and leaf plot show the distribution of these data? Okay, so let's do this. I'm going to draw a vertical bar. What that does is separate the stem, each stem, from the leaves. Now, I need to look at my data set. In this case here, the lowest data value that I have is 68, and the highest is 100. So my stem is going to start off with the number that's in the tens place. That's the first digit, the 6. And then I'll write 7, 8, 9, and 10. So these are my stems on the left side. On the right side, I'm going to have my leaves. So now, this 6 represents data values between 60 and 69. So I need to find out, do I have a data value that's between 60 and 69? And I do. That's 68. So here, the leaf, which is going to be the last digit in that number, that goes behind this vertical bar. So here, this represents a number 68. And then for the 7, that represents 70 to 79. I'm going to find the data values that are between 70 and 79. And I do have 2 of them, 72 and 75. Now we want to put those in numerical order. So the 2 has to go first for 72. And then the 5 has to go next. Okay. And then the 8 represents data values between 80 and 89. Well, looking at this, I got 89, 89, 88, and 86. Okay, so the smallest is 86, so that 6 would be your leaf for the 8, for the stem of 8. And then the next highest is 88. And I have 2 data values, 89. So I need to write that leaf twice. That's the 9 and the 9. Because I have to account for each and every single data value. So that's why I wrote that 9 twice as my leaf. And then the 9 represents data values from 90 to 99. And I only have 2, the 90 and 98. The 90 is the smallest, so I'll write a 0 for that leaf for 90. And for 98, I write down the 8. And then finally, for 10, this represents data values from 100 to 109. I only have 1 data value for that, and that's 100. So I write down the leaf, which is the last digit in 100. That's 0. So this is what my stem and leaf plot looks like. Now, let's count how many data values I have here. I got 2, 4, 6, 8, 10. That means the number of leaves should equal to 10. Here I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's very important. So if the number of data values that you have here do not equal to the number of leaves, you messed up somewhere. So it's very important that the number of leaves in this stem and leaf plot has to be the same as the number of data values in that set of numbers. All right, here's another example. The data represents the height of eruptions by a geyser. Use the heights to construct a stem plot. Identify the 2 values that are closest to the middle when the data are sorted in order from lowest to highest. Oh, let me go back to the example 1. I apologize. How does the stem and leaf plot show the distribution of these data? Okay. Well, if you look at this, the lengths of the rows are similar to the heights of those bars in a histogram. and longer rows of data, correspond to higher frequencies. What that means here is this, and this makes sense here, because if I took this paper like this, you're going to see these stems will represent those values on the horizontal axis, and these leaves represent the height in the histogram. Okay, so that stem and leaf plot does look similar to the height of the bars on the histogram. Okay, now example number 2. Okay, here we got the data representing the heights of eruptions by a geyser, and then we're going to use the heights to construct a stem plot, identify the two values that are close to the middle when the data are sorted in order from lowest to highest. All right, so let's construct our stem plot. Okay. Oops. Let's see, the smallest number is 34, and the highest is 90. So I know the smallest stem is going to be 3 for the number 30, for 30 to 39. And then 4, 5, 6, 7, 8, and 9. Okay, now we need to find out what our leaves are. This 3 is for 30 to 39. There's only one number, and that's, in this case, 34. And then the 4 represents data values from 40 to 49. There are two numbers here. There's a 40, and there's also another 40. So I'm going to need 2 zeros to show that I have two data values that are 40. And then for the 5, that's for 50 to 59. Let's see here. I do have a 50, a 57, another 50, a 55, and another 50. Notice I got 3 50s here. So let's start with that. I need 3 zeros to show that I have 3 numbers that are 50. And then I got 57, and then I also have 55. Let's start with the 5 first. I'm putting these in numerical order, and then the 7. And then for the 6, that represents the data values from 60 to 69. Let's see here, we got 69, a 66, a 68, a 62, and a 60. All right, let's start with the 60. That's the smallest. So I put 0 there, and then 62 is the next. And then 66, then 68, and finally 69. And then the 7 represents data values from 70 to 79. Well, you got 71, a 70, another 71, and another 70. So I get two numbers that are 70. So I need 2 zeros there. And then 71, I got 2 of those. I need a 1 and another 1. And then the 8 represents the data values from 80 to 89. In this case, I do have an 80 and an 86. So let's put 0 there for the 80 and a 6 for the 86. And then the 9, there's only one number, 90. So 0 there for the 90. So that's my stem and leaf plot. Now, we're going to use the heights. Now, we're going to identify the two values that are close to the middle. Identify the two values that are close to the middle when the data are sorted in order from lowest to highest. Now, the way I would do this is cross out the highest and the lowest data value and keep crossing out the highest and the lowest data value until I get to the middle number. So if I do this, if I cross out the 4 and the 0, this 0 and this 6, this 0 and that 0, 0 and this 1, that 0 and 1, the 0 and this 0, this 5 and this 0, the 7 and this 9, the 0 and the 8. Notice the two middle numbers are right here. The 2 and the 6, those are my stems. So, and they're both in the 60s. So here, 62 and 66 are closest to the middle. And when we get into chapter 3, we're going to be talking about a term called the median, finding the median of a set of data values here. But this is just my technique of finding the two middle numbers. So 62 and 66 are close to the middle. Okay. All right, next we'll look at a bar graph. So this is what a bar graph looks like. It uses bars of equal width to show frequencies of categories of categorical or qualitative data. So there's another definition. Qualitative data is considered to be categorical data because you're dealing with categories here. And in this case, we're dealing with these individual decades from 1950 to 2010. Okay. The vertical scale represents frequencies or relative frequencies. The horizontal scale identifies the different categories of qualitative data. The bars may or may not be repeated by small groups. A multiple bar graph, like this one that you see here, has two or more sets of bars and is used to compare two or more data sets. So like in this case here, in this multiple bar graph, the dark blue represents the male, the pink represents the female. And this deals with the median income by gender. Okay, so that's what a bar graph looks like. Now we won't do an example of constructing a bar graph, but just do be familiar with what it looks like. And also we can use technology to create a bar graph. All right, next is a Pareto chart, and it looks like this. This is also for categorical data, with the stipulation that the bars are arranged in descending order according to frequencies. The vertical scale represents frequencies or relative frequencies, where the horizontal scale identifies different categories of qualitative data. So here the bars, as you can see, decrease in height from left to right. Okay. So that's what a Pareto chart looks like. All right, next is a pie chart. It is a graph that depicts categorical data as slices of a circle, in which the size of each slice is proportional to the frequency count for the category. Okay, and this is what a pie chart looks like. Okay, now we won't do a pie I won't have you constructing a pie chart in this course because of the fact that you have to create one from scratch, and it can be a little bit complicated and time consuming unless you have technology that will do that for you. Okay. And here, one suggestion from a graphic expert: never use pie charts because they waste ink on components that are not data and they lack an appropriate scale. So you can see here when I printed this off, I used up a lot of ink here for this piece of the pie. Okay. So that's why it's important that you never use a pie chart because of how much ink it's going to take. All right, next we'll look at a frequency polygon. And we're going to look at a couple of examples of constructing a frequency polygon. It uses line segments connected to points located directly above class midpoint values. A frequency polygon is very similar to a histogram, but a frequency polygon uses line segments instead of bars. So here, this is an illustration of what a frequency polygon looks like. Okay. Now here, a variation of the basic frequency polygon is a relative frequency polygon that uses the relative frequencies or proportions or percentages for the vertical scale. In this case, we're just using the frequency. But for a relative frequency, we of course use a percent. So on the next page is another example of a frequency polygon, comparing high lead group and low lead group with IQ scores. Okay. All right, next let's look at example 3. Here we're given, the given data represents the number of people from a town aged 25 to 64 who subscribe to a certain print magazine. Construct a frequency polygon, and does the graph suggest the distribution is skewed? And if so, how? Okay, so now let's draw this frequency polygon. So here's my vertical axis and on horizontal axis. Now in this case here, my vertical axis is just going to be the number of people. And I'm looking at from 72 to 772. So let's do this in increments of 100. This will be 100, 200, 300, 400, 500, 600, 700, 800. These represent the number of people. And I have like 4 classes. It represents the age. Now we're going to use class midpoints. If you recall, when we do a class midpoint for each class, we add the lower class limit and the upper class limit together and divide by 2. So if I do 25 plus 34, I'm going to bring my calculator up here. So if I do 25 plus 34, that will give me 59. 59 divided by 2 would be 29.5. So the class midpoint for this first class would be 29.5. Now I can do the same for the other 3 classes. But if you look at this, the class width, if you recall, the class width We find that by taking the difference between any two consecutive lower class limits. So if I do 35 minus 25, that would give me 10. So my class width there would be 10. That's the difference between any two consecutive lower class limits. So let's add 10 to this 29.5 to get the next class midpoint. That's 39.5. And add 10 to the 39.5 to get the next class midpoint. That'd be 49.5. And then add 10 to the 49.5 to get the next class midpoint. It'll be 59.5. Okay, so that's my graph. I mean, that's my axes. Now let's do the frequency polygon. I'm going to draw a point right here at this point of intersection for the horizontal and vertical axes. Now at 29.5, that's the class midpoint for 25 to 34. It's 72 right here for the number of people. So I'm going to have to guess right here. So 72 will be about right here because it's less than 100. And 39.5 is the class midpoint for 35 to 44. The number of people there is 159. 39.5, so 159 will be about right here. And 49.5 is the class midpoint for 45 to 54. The number of people there is 772. So that point's going to be way up here somewhere. And then 59.5 is the class midpoint for 55 to 64. The number of people for that is 506. Let's say about right here. Now I'm also going to draw on this horizontal axis another mark. If I add 10 to the 59.5, since the class width is 10, that'd be 69.5. And the reason why I'm doing that is this. A polygon is a closed figure. That means I need to have this whole polygon closed. I can't have any open spaces there. Okay, so that's why I drew this point right here at the intersection of the vertical and horizontal axes. So all we do there is just simply connect the dots. Okay. So that's what a frequency polygon looks like. It is a closed figure. Okay. So that means this part and that part has to be closed off. Now, does the graph suggest that the distribution is skewed? And if so, how? Well, if you look at this graph, it does appear to be skewed in this case. Now, we did talk about skewness in the last videos of section 2.2. So here it is skewed to the left because it has a long left tail on the left side. So we can say here that the distribution appears to be skewed and knows where it's skewed to the left. And if it's skewed to the left, we can also say that it is negatively skewed. Okay. All right, here's another example of a frequency polygon. You'll have to excuse these dots that I have here. I'll have to wipe those out. Okay, says here, the given data represents a frequency distribution of the F-scale intensities of recent tornadoes. Use a frequency distribution to construct a frequency polygon. Does the graph suggest that the distribution is skewed? And if so, how? Okay, so let's look at this. So here's the axes, the vertical and horizontal. Let's see, from 27 all the way down to 1. Let's do these in increments of 5. So this will be 5, 10, 15, 20, 25, 30. And of course, my tornado F scale is from 0 to 1. So I'm going to put 0 here, 1, 2, 3, and 4. Okay. So in this case here, I'm going to draw a point right here at this intersection of those two axes here. All right. For the 0 F scale, there were 27. The frequency was 27. So here I'm going to go up here to close to 30. Or actually halfway between 25 and 30 and draw the point. And then for 1, that's 16. So at 1, I'm going to go up a little bit past 15. Okay. And then for 2, it's actually 2. So it's a little bit less than 5. So I'll say about right here. And then for 3, the frequency there was 3. So it's a little bit up here, less than 5. And for 4, it's 1. Which is about right here. And then I'm going to draw another mark for the 5. We know that there's no F scale of 5 listed there, so I'm going to put a dot there on the horizontal axis so that way I can close off my frequency polygon. Okay, so the next thing I'm going to do is connect the dots. From 4 to 5. Okay, so there's my frequency polygon for this. Now, does the graph suggest that the distribution is skewed? And in this case, it is. Okay, and if you look at it this time, it is skewed to the right because it has a right long tail. The long tail is to the right. So that means that this distribution appears to be positively skewed. or we can say skewed to the right, because it has a right long tail, as you can see. Okay. So that is how we construct a frequency polygon from a frequency distribution. Okay. Another type of graph that we can look at is an ogive. We'll just talk about this one. We won't do an ogive here. Okay, it is a statistical graph which depicts cumulative frequencies. Ogives are used for determining the number of values below some particular value. An ogive uses class boundaries along the horizontal scale and uses cumulative frequencies along the vertical scale. So if you look at the graph at the top, you'll see this is what an ogive looks like. Notice in the vertical axis, you'll see cumulative frequency. So you will have to do a cumulative frequency distribution in order to construct what they call an ogive. Okay. All right, now let's go ahead and talk about graphs that are deceptive or that can be deceiving. Some graphs deceive because they contain errors, and some deceive because they are technically correct but misleading. It is important to develop the ability to recognize deceptive graphs, like in this case, a non-zero axis, where the axis begins at some point other than zero, so that differences are exaggerated, okay? So if you look at the one on the left, you'll see they started the vertical axis at 30. So here, this graph looks deceiving. But if you start at 0, then this graph does make sense. By the way, this is the highway fuel consumption with the vertical scale starting at 0. Okay. This would be the correct way of doing it. The incorrect way is the one on the left, because people are going to think that for a Honda Civic, you get more highway fuel consumption than the Chevrolet Aveo and the Toyota Camry. Okay. All right, next is a pictograph. This can also be deceiving as well, because in a pictograph, you're drawing objects, and they also can be misleading, as I mentioned. Data that are one-dimensional in nature are often depicted with two-dimensional objects or three-dimensional objects. With the use of pictographs, artists can create false impressions that grossly distort differences by using these simple principles of geometry. And that's this: when you double each side of a square, the area of the square doesn't merely double, it increases by a factor of 4. And the second, when you double each side of a cube, the volume of the cube doesn't merely double, it increases by a factor of 8. Now let me explain what that means here. Let's say I have a square. Two inches on each side. Okay, if I find the area of that square, that's of course the length times the width. So in other words, 2 times 2. That's going to be 4 square inches. Let's say I doubled that square. And this is not drawn to scale. So this time it's 4 inches. And this time it's also 4 inches. I'm doubling this. So if I take the area of that, the area will not double. This is going to be 4 times 4, which makes that 16 square inches. So here the area does not double. It actually increased by a factor of 4. the area has multiplied by 4. It does not double. Okay. So do be aware of that. Okay. Now the next page is an example of a pictograph that looks deceiving in this case. Okay. Because here in 2013, 18% of users of US adults smoke. And then on the left side, you got 37% of US adults smoke. Notice that the cigarette is blown up bigger than this one. Again, that can be deceiving, so do be aware of that. All right, so when examining data depicted with a pictograph, determine whether the graph is misleading because objects of area and volume are used to depict amounts that are actually one-dimensional. Okay. And I'll end with some important suggestions from a graphic designer named Edward Tuft. And it says here, for small data sets of 20 values or fewer, use a table instead of a graph. Number 2, a graph of data should make us focus on the true nature of the data, not on other elements such as eye-catching bar, distracting design features. And number 3, do not distort data. Construct the graph to reveal the true nature of the data. And finally, almost all of the ink in a graph should be used for the data and not for other design elements like that pie chart that I showed you, because he does recommend you not do a pie chart because of how much ink that it takes to even create one. Okay, so that will end this video on section 2.3. And this video does deal with graphs that enlighten and graphs that are deceiving. Okay, so hopefully this will be enough to help you complete the homework assignment. And also feel free to email me if you have any questions or concerns.